Okay. Okay, so the question was that on some of the homework, you're given questions like this, and they want you to find the E of the cell using the reduction potentials, okay? And from cathode minus anode, right? And so the observation was made that here you actually have to figure out what's being oxidized and what's being reduced. Because if you look at the reduction potentials, then this doesn't follow suit with those, right? And so here we're going from gold to gold 3 plus, so that means we're losing 3 electrons, okay? And we're going from calcium 2 plus to calcium, so we're gaining 2. But then it's a balanced chemical reaction, so you have to have 3 calciums and you have to have 2 golds to be able to balance those into 6 electrons total. Okay, that are being lost and gained by those two things. So if we look at the reduction potential chart, which let me see, pull that up. Okay, so we want to look at it for gold. It's always so fun to find everything on here. They should put it in alphabetical order. No, that wouldn't work. What's that? There it is. Okay. So we have gold 3 plus is a positive 1.5. Okay, so this is a plus 1.5, right? And here, what was it? It was calcium, right? Calcium negative 2.87. Negative 2.87. Volts. Okay, now if we looked at this and we were going to say cathode minus anode, then how would we set it up if you weren't considering the reaction? Let's take. Okay, so we'd say.
No, you can't just always do that. Well, I know, but you said like.
Yeah, if we were going to set it up, just so what I'm saying is what they're saying. If you were going to set it up, you would say more positive thing minus the more negative thing, right? Okay. So we would say 1.5 minus a negative 2.87 volts, okay? And what would that give us? 4.37, because it would be a negative plus a positive, so we get a 4.37, okay, in this case, which would be spontaneous, right? That would be a spontaneous process. But as we know, chemical reactions don't have to be spontaneous. We can cause them to go in the reverse direction. So through electrolysis, we could actually do the non-spontaneous reaction, okay, and go from instead of reducing, so the spontaneous process would actually be this, whoops, that's not what I wanted to do. What's this? Calcium. Okay, so this is how we just calculated it for this process, right? Going from gold 3 plus to 3 calciums, and that would be if I had a cell and I was hooked up to it, a voltaic cell, then this process would be spontaneous if I had gold being oxidized by calcium. Okay, so gold being oxidized by calcium. So, but that's not what we see here, right? Here, gold is being reduced by calcium. Calcium is stealing electrons. I'm sorry, calcium is, yes. I'm sorry, I'm saying this all backwards. So gold is being oxidized. Gold is oxidized, right? It lost electrons. It was oxidized. And that means gold is the reducing agent. This one was reduced, which makes this the oxidizing agent. Okay? So we have that process is different than this one, where gold here is being reduced and calcium is being oxidized. And this is the spontaneous process. So we have calcium is the reducing agent and gold is the oxidizing agent. Okay? So the way you have it set up in this equation would be the spontaneous process at 4.37 volts for gold being reduced by calcium, okay, which is the reducing agent. So we would have the 1.5 volts here and the negative 2.87 volts here, okay? So because gold was reduced, okay, it is the cathode. So the thing that's reduced, reduction minus oxidation, in other words, okay? But for the top reaction, we have to switch that, right? Because now we have reduction minus oxidation in the reverse direction. E naught of the cell equals cathode.
What are you switching?
What I'm switching are the numbers. Reduction minus oxidation. Okay? So in the top reaction, what's the reduction is occurring on the calcium. So that number needs to go first. The 2.87 volts. Okay? Negative 2.87 volts. Minus the gold, which is being oxidized, is plus 1.5 volts, which is a positive 0.5 volts. Okay, and in this case, we get E naught of the cell equal to what? Negative 4.37, is that what it was?
Yes.
4.37 volts, which is exactly the opposite direction, basically, right? So
After all that being said, basically we just have to figure out from the reaction we're given, we have to figure out what's being reduced. We can't just take the more positive. Like
if they told you this, okay, which they do this sometimes, okay, so they'll say E naught. They want you to calculate the EMF or the E naught of the cell for a AU3 plus okay, cell, and then you could just take the spontaneous. It'd be for the spontaneous process that they're talking about, and then so but here they gave you the reaction. And they're saying whatever's reduced is your cathode, whatever is oxidized is your anode.
What was the thing at the bottom? Can you explain what you said at the bottom?
So it doesn't matter which way those are going? Since well, those are both being reduced. AU to AU3 plus, CA to CA2 plus. Because the one example you gave us said AU to AU3 plus and then CA2 plus to CA. Just like
Actually, I think it would be written.
Yeah, so then we still have to figure out which one's being reduced, which one's being
Yeah, 'cause I
oxidized.
think we did an example like this.
We did it just
in
like that.
class, And we had to write the
switch.
equation out ourselves.
Right.
And it was given to us like that. So, okay, so basically, we probably should not be remembering it as positive minus the more negative. We should just be remembering it as
Cathode minus.
the reduction minus the oxidation.
Reduction minus
Right.
oxidation will give you the correct way each time.
Right. So reduced minus oxidized. That gave
Reduction minus the oxidation, yes. The
Give us the-
reduction is the process of losing electrons. So that's why it's the more positive.
Reduction.
You're losing those, gaining those electrons, okay? Reduction is a process of gaining those electrons. Oxidation, you're losing those electrons. So electrons are flowing
Minus oxidation.
this way, okay? So reduction minus oxidation will get you there every time.
The other way, a little secret to do it, is I think if it's switched in here, you switch the signs and just add them.
So they didn't give you both answers, positive and negative. They didn't. Okay.
And the way we were,
So you
the way we were learning gave us the positive, and the real answer was negative.
right. So what I'm concerned about is what did you just say about just switch the sign?
So for this one right here, it would be AU3 plus is 1.5,
Oh, okay, I see what you're saying. I just wanna see how the columns are.
right? Or is it AU to AU3?
This is 1.5.
So that's 1.5. And then so CA is CA2. Oh, see, that
This is like, this is all me. Yeah.
She didn't know what she was doing. She didn't know. But then that one would be.
But I think it's for equilibrium.
Yeah, it doesn't work.
Like, so, like, on the chart.
I don't know. I'm just doing reduction.
It doesn't show it.
Somebody had
One of
shortcuts,
these,
yeah, but
it doesn't show.
I don't know how she's not
Like, one of them, but it's the same
I
thing.
think she was
Yeah,
doing,
yeah,
she,
you still get the same
instead of
thing. So,
doing
yeah.
the positive
I just
1.5,
wrote-
she did negative 1.5.
No,
So
right,
she did
yeah.
minus
This-
positive
this
2.8.
was a chart.
You can't switch these signs. You can't switch the signs on those.
Oxidation, so this would be
No,
this
yes.
minus this.
Because I mean, in the PowerPoint it says,
Or that reduces
in the PowerPoint right thing, it says switch the signs. Because
Yes.
if it says CA2 plus 2 electrons to CA
That's
solid,
why I was messed up.
like the opposite of that, then it says just switch the sign.
Okay, good to know.
But then that doesn't work, does it?
So this is chapter.
No, you're not supposed to switch the signs. The PowerPoint says that.
Yeah, it's a
What chapter is it? 17? This chapter should just be dropped. Well, because.
Guys, there's a lot of stuff that you've learned in this chapter.
We don't need it.
Okay, so where is it saying it?
Here we go, right here, number 14.
So what you have to do
It
is.
says the sign of E naught changes when the reaction is reversed. Oh, no, that's.
The E naught, sign of E naught.
Yeah.
And we just proved that, right?
Yeah.
But you don't switch the sign of the reduction potentials. They have to stay the same always, okay? You don't change. You don't change the sign of that, and you don't change the magnitude of it with the stoichiometry. None of that changes. The sign of E naught will change. We just showed that. Okay, depending on which way you're going For the spontaneous reaction, it'll be positive. For the non-spontaneous reaction, it will be
How do
negative.
you tell that from just looking at
What do you mean? Look, they'll give you the chemical. They gave you the chemical reaction,
it?
right?
How do you tell that that's, that you need to switch that sign? If you do the more positive minus negative.
You don't switch the sign.
On the E naught,
We
there's-
didn't switch the sign, right? We did not switch the signs, and we got the negative E naught. We calculated the negative, but we didn't switch any signs.
Well, you switched the numbers.
I switched the numbers because the reduction and oxidation was switched.
But I'm saying the way we've been doing it is you can't, I mean, you can't really.
Well, the way we were doing it was the spontaneous process every time. We're talking about the spontaneous process every time. Because it was higher on the list, it's more positive, so it had a higher reduction potential. So we were talking about that spontaneous process. That's how we were calculating it,
But if
right?
we, I mean, using that way.
But if they tell us we're going to do the reverse reaction through electrolysis,
If it went from 0 to
we're gonna push those electrons backwards through electrolysis. We're adding the energy, the non-spontaneous process. We're going backwards.
But I'm just saying, looking at that reaction, we can't tell that we're doing the opposite. That we're doing the non-spontaneous, right?
Yeah, but then.
Right. So that's why we decided it was better to go with reduction minus oxidation.
That's what I'm saying, like, the way we've been doing it, there's no way we can tell.
Not from there. You're right. You're right. That's why everybody's confused, right?
Right.
So we're saying that if you come across a question like this, okay, then the best way to look at it is reduction minus oxidation. No. It's not reduction minus oxidation agent. If you want to do the agents, so you see how gold.
He switched it. That's the switched equation. The original equation doubled a little bit more.
Oh yeah, this is not the one that goes with this equation. I'm sorry, that's confusing, right? Yes, that's not the. This is the one down here. Up, the one up here. Well, you would switch the place because they're going the other way. So whatever was, they're doing the exact opposite thing. Yeah. If the reaction is going the other way, then you just switch the numbers, and you'll end up with the negative instead of the positive, which means the non-spontaneous process.
The answer is supposed to be negative because it's non-spontaneous, so is that why you changed it? Because it got positive?
Getting reduced minus getting oxidized.
Yeah, that's how you're supposed to find out. Yeah.
Should we ask?
So I'm trying to make sure I answer your question. What?
Like, so when we started off, it was positive, right? So that's the spontaneous. So if it's spontaneous, that means we have to like switch the coefficients in order for the answer to be non-spontaneous. So for it to be negative.
You have to look at your equation. Okay, let me rewrite this equation. 2Au plus calcium 2 plus 3 of them yields 2Au3 plus calcium solid aqueous solid. Okay, so what we're saying you should do, and when you're given this equation, you look at it and you ask yourself, what is being reduced? What is being oxidized? Okay, so oxidation is loss and reduction is gain. So which thing lost electrons?
Isn't the gold being
Coming, loss of electrons coming more positive.
so that's gold?
Gold is oxidized. What is reduced?
Calcium.
we're saying instead of doing more positive minus the more negative, which would always be the that would always be the spontaneous process. Okay, a better way to look at it, because you might encounter the non-spontaneous process, is reduction minus oxidation. Okay, so now that we've identified what has been reduced and what has been oxidized, okay, E naught of the cell equals reduction minus oxidation. This is going to get you the right answer every time. Okay, so the gold has a reduction potential of 1.5, and the calcium has one of negative 2.87.
So we'll have negative 287
Minus 2.87 minus 1.5. Okay, and here this equals a negative 4.37 volts.
I think the reduction to oxidation is a lot better than the calculation.
Okay, so reduction minus oxidation.
Reduced, so I get that by oxygen minus oxygen.
Yes.
Reduction.
So look at it over here on this side of the equation, and it's reduction minus oxidation. Okay. Okay, so that is a non-spontaneous process. That's pushing it backwards. Okay, good. I'm glad we could clarify that.
And then number 1 on chapter 7, the balanced redox equation must have.
Yeah, that one there was one that was iffy in there. So if you chose 1 and 2,
Yeah.
and I think it wants you to choose 1, 2, and 3,
Yeah.
but I don't really agree with 1, 2, and 3.
I don't really
But
think three's not right.
if you chose 1 and 2 and got it wrong, just send me an email. I'll give you the credit for it. If you chose 1, 2, and 3 and got it right, then
And
just
then
keep the
same
credit.
with the chapter 16, that one crazy question that we still haven't figured out.
I'm just gonna add points. I'm gonna curve that homework
Okay.
to add points to it.
And then for this one, send it to you.
Yeah, just let me know if you got it wrong,
Okay.
and I'll just. I would never remember that. You have to send me an email, and when I'm sitting at my desk and I can fix it, I will fix it. Okay. Me? I would taught 3 classes this summer. Right now I'm only at 1 because the summer 1's over and the 8 weeks is over. So I'm down to this class. And then school starts really soon. I don't even get a break. We don't get that week off. We work that whole week between prepping for the full semester term. Okay, so what else? What are your other questions?
Well, I'll show it to you. Well, that's okay.
Are we doing the lab review in lab?
Mm-hmm.
So we don't even go over that right now?
No? We'll have a whole 2 hours, 40 minutes in lab for review.
We just stay in here?
We can't because they have a class that starts at 11 in here.
We can kick them out. English.
There's number 11,
What's
and
up?
I was putting everything
We
in,
just had a
but,
conversation about our long.
I was not getting the right answer. So it was just finding
Are
K.
you in? How do you do it? I was trying to. No, I don't care. No, actually, don't even explain it because it's all. Reduce minus oxidize. Remember that.
Just remember ERO, kind of like a hero, but ERO, E cells, RO, reduce minus oxidation. Y'all are going to remember it, trust me though. Y'all are going to be like, ERO.
That's good.
Okay, you say so.
That's good. Oh, arrow.
Oh, you know what? Now that I think about it, I think I know what I did wrong. I was still doing the cathode minus the anode is the more positive minus the more negative, but it could be reversed.
It
Reduction.
is.
So that's what I was getting wrong.
Minus.
It's gonna be I minus DR instead of
Using oxidized. This is reduced.
And the two numbers are right
Oh, you
here.
have them where?
Right here. That's why I was getting wrong. Euro.
You do you. I'm gonna do it the right way.
Wait, well, is this the chapter 17?
Chapter 17, yeah. Number 11.
Those numbers are just from the chart, right?
Mm-hmm.
Yes, but we were just not figuring out the right cathode.
Yeah, no, I think I know what I did wrong now.
We were going with cathode as the more positive one, but cathode is the one being reduced instead of, you know what I'm saying?
That's it.
No, that's not it. But that's the start of this, right? To find K, we got to find E naught of the cell because E naught of the cell equals
So we got it right, right?
E naught of the cell equals what's the equation?
257 over N natural log K.
That's right. Okay. So we want to solve for. I don't have it in front of me.
I don't
So
remember.
is that what it is?
Oh, I do have it in front of me. Stand by.
Yeah, point
Yeah,
0.257.
0.257.
With the log and.
Point zero.
With 0.257.
Like that?
Yep.
Okay.
Perfecto.
Okay, so we need to identify a few things here. First, we need to determine the E naught of the cell. 0.535 minus 1.066.
It's -0.5.
Negative 0.53. Okay. So we get E naught equal to negative 0.531.
Just to make sure real quick, the agents are always going to be on the left, right?
Say it again.
Like
The agents are always going to be on the left, the reactant side. So what was oxidized and reduced is over on the product side. Yeah, so that's how I'm going to figure it out over there. So we'll just work on that side of the reaction.
And N, 2 or?
Well, let's see.
Your number?
Yes,
How?
because to go from Br negative to Br 0, okay, I have to lose one electron, right? But I have two Br negatives to go to a Br 2, so that's 2 electrons.
Then it's the same for the I.
Yep. So the I2 is at 0, and it needs to go to I minus. So I have to gain 2 electrons.
So you don't add them all up, it's just by each half reaction?
Well, the half reactions have to match.
Right. So
The
you
electrons
say,
of the
like,
half reactions
they
have to
would
match.
But it wouldn't be 4, like you wouldn't just add them all together.
No,
Okay.
no, because it's not electrons. It's not a sum of electrons. It's 2 electrons being lost from one place and being gained by another place. You can follow the electrons. Where did they go? They went from Br. Those 2 electrons from Br went to where? They went to I2. These 2 electrons flowed here to E minus. They flow this way. Okay? So Br negative loses those electrons and I2 picks them up and becomes I2 minus. Or 2I minus, excuse me. Okay? Alright, so did you guys solve? So here we're going to solve for K. We know the E naught of the cell. We're going to multiply it by 2 because that's the number of our electrons. So 0.531 negative times 2. And then we're going to divide it by 0.0257, and it's the E of that.
You just math.
Okay? Are you getting it now? Did you do this?
Yeah, no,
What
that's
is it?
exactly what I did, except for I was still doing the more positive minus
Right.
the more negative.
Okay.
So I was getting completely wrong.
Right.
That throws it completely off. Because we were doing it the regular way.
Right.
And 0.531 instead of negative 0.5, and that throws everything.
Okay.
Yeah.
So R minus O, that's gonna help, right?
Yes.
Okay.
All right, all right, all right.
Okay, R minus O.
Bro.
Rho. You guys always love. Okay, so what is this? What is this? The E of 2 times 0.531 negative divided by 0.0257.
Oh, 5.7 times 10 to the negative 19.
5.7 times 10 to the negative 19. Okay, so that is our K for this reaction.
So there's some questions where you need like KSP and the Q and that. Are we gonna have that chart, or would you on the test would it just provide the KSP?
Like you had to look it up.
Like we had to look it up in some of the homework questions. This was I don't know a couple chapters ago. Just came up. ADD.
I don't think there's anything that you would need. I think that it's provided in the question.
Okay.
So you're talking about if you're in chapter
It's gonna
15 and you're trying to figure out
if
the
it's a precipitate or not.
yeah.
And you need to know, you gotta find the QSP and you gotta compare it to the KSP, but it didn't give you the KSP. We had to
Right.
look it
You
up.
you would need to be given those, yeah.
Okay.
So they'd be in the question, and if it's not, then just ask me, and I'll find it for you.
Any questions?
700. Yeah, 1 hour.
Well, yeah. It's going to be probably around 30 or 40 questions.
How much will it cost to cut that in half?
See, I struggle with that because if I cut it in half, then everything's worth 5 points, right? So,
Well, you can just make it out of 0, and then everything's just bonus. So I mean that's.
oh yeah, that's great. You guys have such great ideas. I swear, you guys could be used car salesmen and be very good at
I was
it.
a Marine Corps recruiter for 4 years. I pretty much love that you go.
Okay, what else do we need help with? Are you guys okay on chapter 13? Rate?
Boy, shit, I forgot about that.
I've really been focusing on the first.
I can bring one to lab.
Let's do one of those styrofoam.
Oh, I got a question. That reference material,
One of those?
can we print that out and bring it? Because I hate computers and going back and forth and all that crap.
If we show it to you.
Can we show
How
it to you?
about I bring some printed copies?
Yeah, that
Yeah,
works
that
better.
is
If you're like
perfect.
flipping back and forth on your pages, it's super.
Yes.
That's what he's thinking.
Yeah, yeah. I was gonna say we could show it to you before we go, but
Well, I can bring some.
that would be easy. Plus then it doesn't waste money.
Waste this your tuition schooling.
Yeah, exactly.
We do an equation, like, we have to balance it with the redox, but it's like with the waters and hydrogen.
Sure. Do you have an example?
Wait, I have one
What
right
are
here.
the base and what are the acids?
With basic or acidic?
17?
Where they want to do one of each.
Oh, no.
Second,
I can find them.
That was a whole.
Yep.
This is all just E stuff. Oh, I'm there. There it is.
13 on
Okay, so then this one is H2S plus HNO3 gives us S plus NO. And that's an acidic solution.
Okay, let's start with that. It's just one S?
Yeah, yes.
S solid?
Doesn't say.
Doesn't say? Okay, probably doesn't matter. Okay, but it's just one S. All right. You don't see that a lot. S4, something like that. But whatever.
Well,
Okay.
HNO3 is a negative 2.
Thank you. NO3 minus, NO2 minus, NO1, right?
HNO3.
None of them have.
Shit. It doesn't have, oh, it's just going to, it's not, it's, okay, no charge. Okay, it's fine, that's fine. Okay, so H2S going to S is our first half reaction, right? And then HNO3 going to NO is our second half reaction. And this is in an acid solution, which means we don't have to continue on. We're going to have to just do the full process and then stop. We'll be done. If it was in a basic solution, we would do the full process, and then we would add hydroxides at the end, okay, and form waters and etc. All right. But here we have this process. So I have to, here I have to add hydrogens, okay? I don't have to add oxygens, just hydrogens, okay? So in the first one. So if I had to add oxygens, I would need what? Water. But here I'm just adding hydrogens in an acid solution, so I'm just going to add what? H plus.
So always in an acidic solution, you only add H?
Or water if it's for oxygens, okay?
So you only add the water when you're needing oxygen as well?
That's right. Okay.
And then for basic, it's H and OH?
Get that water.
In the basic solution, you do it exactly the same way you do it for acid, but then you finish it adding hydroxides at the end. Okay?
So you can put H2Os, H's, and
What's up?
all of them? Is that what you're saying?
In the basic, you would. Yes, you would too. H2O, H's, and OH's. But you wouldn't do the OH's until after you've balanced everything like you would for an acidic solution. Okay? All right, so everything's balanced right now in this first half reaction by mass, or we should say by element, okay? But we also need to now consider the number of electrons that are being transferred here, okay? So on the top, we're going from S here to minus to S0. So did we lose or gain electrons? We lost electrons. Where do I write them if I lost them?
Right.
As a product. On the right. Okay? So plus 2 electrons there. HNO3, what do I add first? I need to add some waters because I have to balance the oxygens, and I need two extra oxygens. I only have one, I need 3.
Why do you need two?
Because you need 3 oxygens.
Okay, so I have 3 oxygens over here, and I only have 1 right here. I need something else to add oxygens. I need the water. Okay, so I need 2 more oxygens there. All right, so now that I have 2 waters, my hydrogens are not balanced. I have 1 hydrogen from the HNO3. So I need to add, I need a total of 4. I feel like we did this example once. Did we do this one? No? So I need 3 more H pluses to balance those. Okay? Now, yeah, I swear we've done this one. Or maybe I did it with somebody else individually. Okay. Okay, so we need to figure out how many electrons are being transferred That's going to be from the nitrogen because nothing else is changing oxidation state. The oxygens are staying -2, the hydrogens are staying +1. So what's changing oxidation state is the nitrogen. So what is the charge of the nitrogen here? What is its oxidation number in HNO3? +5. Okay? Who needs me to go over that?
Me.
Okay, so we have oxygen is -2. There's 3 of them. So that's a -6 charge from the oxygens, right? We balance one of those charges with the hydrogen. That leaves us with 5 more charges. So we have a +5 on the
I
nitrogen.
just need time to like,
That's okay.
so.
Okay, but that's a very important thing that we have to be able to do here is be able to identify the oxidation state of the elements in these compounds, okay, because they're changing. Okay, so Andrea, what is the oxidation state then of the NO, the nitrogen and NO?
And it would be 2.
+2, right? So we're going from a +5 to a +2. How many electrons is that? Okay, that's 3 electrons. Where do I add them? That's right. I have to add them as a reactant, which I don't have room, plus 3 electrons. Okay? All right, so everything's balanced, but now we have to balance them between each other because they're reacting with one another. So the number of electrons that are being lost here have to match the number of electrons that are gained here. Okay? So they need to be the same for this reaction to work. So I need to make the number of electrons being lost and the number of electrons being gained the same. So I have to multiply the top equation by 3 and the bottom equation by 2. So I'm going to say 3 H2S's, 3 S's, and 6 H pluses gives me 6 E minuses. That's on the top. So I multiplied everything by 3. Now on the bottom, I'm going to multiply everything by 2. So that gives me 6 electrons. It gives me 6 H pluses. It gives me 2 HNO3s. It gives me 2 NOs. And it gives me 6 waters. 4. Oh, by 2, right? I was doing it by 3, so sorry. 4. That's 1. Yeah, that's better. And 4 waters. Okay, now I'm going to combine those into my final equation. Okay, and I'm going to get 3 H2S. Because the electrons are going to cancel, so they're not going to be in the final equation. Plus 6 H plus.
You can't cancel the hydrogen because they are both equal. So you have 6
They do. They cancel. 6 and 6. You're right. So we have 3 H2S's plus 2 HNO3 produces 3S plus 2 NO.
Wait, and then you cancel the H's out?
I did because there's 6 on each side. So
When the H's are equal, you just cancel them.
anything that's equal, anything that is equal on both sides of the reaction, you cancel out. Anything that is the same on both sides of the reaction, you add together. Okay? Okay, so that's our balanced chemical equation there. You want to do one in a basic solution too, right? Okay, do we have an example for that?
It's MnO4 negative plus I negative.
Okay.
Gives us MnO2 plus IO3 negative.
Like that? Okay. So we have MnO4 minus going to MnO2. We have I minus going to IO3 minus. Okay, we want to, I need to give myself more room this time. MnO4 minus 2 minus 2 minus. Okay, I want to balance these. So the top one, what am I deficient in? Oxygen. I am deficient in oxygen, so I have to do what? Add 2 H2O to get 2 more oxygens. Okay, that will give me a balance of the oxygen. The manganese are balanced, so I'm okay there. But my hydrogens are no longer balanced, so I'm going to have to add 4 H pluses over here to balance the hydrogens. Okay, oh, this isn't base, yes. Let's clarify that. Okay, so the top, I've got everything balanced. Okay, now on the bottom one, oh,
Why can't you just add oxygens? Wait,
I'm sorry?
why can't you just add oxygens? Make them equal instead of H2O.
Because oxygen isn't available. The water's what's available to us in these
Oh, so
reactions,
we can't
in these
add
acid-based
oxygens either,
reactions.
right?
What's that?
We can't add oxygens either. It's either OHH or H2O. Those are our options.
That's right.
That's a good question. Can you just add, since it's in a base, can we skip the water, just add some OHs?
Mm-mm.
No.
No, you have to do that. You have to go through and balance it just like you would for acid,
Right.
and then you add it.
That'd be too easy.
It would be. I know. It has to be complicated, right? Okay, so I minus to IO3 minus. What am I lacking now? Or what do I need to add? I have to add oxygens by adding water. So I need 3 H2Os, right?
Electrons up top.
And then I need to add some hydrogens on the other side. 6 H pluses. And now it's balanced on both. Now we have to figure out the electrons. Okay? So what element is changing oxidation state on the top reaction? Manganese. Okay? So what is the oxidation state of manganese in MnO4? Okay, so we have -8 from the oxygens, so that, and we have 1 left over, so that means this has to be +7. MnO2, manganese goes to an oxidation state of +4. Okay?
So, question, when do you add OX minus ions, the hydroxyl ions?
When do I add those? After we've balanced it in the exact same way that we just balanced the earlier one for acid. So we don't do anything different until we're finished. Once we're finished, we add hydroxides. And the hydroxides will equal the number of hydrogen acid molecules that are left. H plus ions, okay? All right. So from +7 to +4.
How did you get +4 and then 2?
Sure. We have a -2 for oxygen. There's 2 of them, so that's -4, which must be balanced by a +4. Okay? Okay, so everything else is the same. Now let's go to the bottom. Oh wait, how many electrons is that? Okay, where do I write them? I gained electrons there, right? I gained electrons. So 3 E minuses is what I gained. Okay, now let's look at this bottom reaction. 3H2O plus I minus. I'm going from a -1 to what? Plus 5. Okay, so we're going to go from negative to 0 and then to 5 more.
Wait, what?
Right? To go from -1 to plus 5, that means we lose 1 electron to go to 0 and then 5 more to go to plus 5. So that's a total of 6
What are you
electrons.
looking at right now?
This one. This is I minus 1 to plus 5. Okay? So that means I lost 6 electrons. Okay? So, now I need to make them match. I don't have to multiply both by the same number, right? I just need to multiply the top one by 2. Okay, so we're going to change this to 6, this to 8, 2, 2, 4. Okay, and now we have the same number of electrons that we lost are being gained. Okay, we lost 6, we're gaining 6, so it matches. So we'll be able to eliminate those. Okay, so in our final reaction now, we're going to write, we're going to get rid of the H pluses on, we're going to get rid of 6 H pluses here, so this is going to be reduced to 2 H pluses, okay, because we got rid of 6 of them. So we got 2H plus 3H2O plus 2MnO4 plus I minus. Oh, I'm sorry. That's right. So I'm going to go ahead and get rid of this water. Thank you. These waters are at 3, so they're going to cancel, and this is going to go to 1 water right here. Okay, so we don't really need a coefficient. So we're going to say 2MnO4 plus I minus produces 2MnO2 plus H2O plus iO3 minus. Okay, now I'm at the point where I'm going to add the hydroxides, the OH minuses. So, do you see how I have 2 H pluses here? So this is the rule. However many H pluses you add the same number of OH minuses to both sides of the reaction. Okay? So it's going to be 2 OH minuses here plus 2H plus 2 OH minuses over here. But these OH minuses turn into what? So I'm going to get 2 waters, 2H2O, okay, which actually is going to cancel this water right here, so I'm going to end up with just 1 water. Is everybody following me? Okay, plus 2MnO4 plus I minus produces 2MnO2 plus iO3 minus plus 2 OH minuses. So we balance it the same way using acid as we would for an acid. And then when we're done, we add OH hydroxides to everywhere that we have H pluses to the same equal amount. Okay, well, we should have H plus only on one side of the reaction. So we add the OH to that side, or we add it to both sides in that same quantity as the H pluses. Okay, so 2 H pluses here, 2 OH minus here, so I add 2 OH minuses here to maintain the balance. These turn into waters, so I had 2 waters. I canceled one of them because I had a water on the other side of the reaction. So I was left with 1 water, H2O plus 2 MnO4 plus I minus produces 2 MnO2 plus IO3 minus plus 2 OH minus hydroxide.
So fun.
Well, you know, if you're gonna have to do anything on this test, that's not too bad. Okay, so hopefully you get a few of those. You don't want any of those? I would take those over a few other things.
Let's just screw pH and just do
I mean, it just.
Well, if it's like, 10 hydrogen ions, then I can do pH.
Okay. You guys share our focus on chapter 17 a lot.
That's because it's the last homework we just did. Let's go back.
Chapter 13. I'm telling you.
What's the enthalpy equation for the enthalpy? Q's.
Oh yeah. Okay. So you want to do a heating curve? Wish I had a. Was there one?
So like one somewhere else.
Oh, what the heck? Okay, chapter 10? No, 11? Dang it. I think it was 11.
Can we do some freezing point?
Yeah, we can. We can do some of those. Okay. This should look familiar, right? So here's a freezing point. Let's see. Osmotic pressure. So colligative properties like osmotic pressure, freezing point, boiling point, vapor pressure, those kinds of things, they are dependent on the number of particles, not on the identity. So if it's a ionic compound, then which of the following aqueous solution has the highest boiling point? Okay, so this first one, C6H12O6, that's glucose. that's a covalent compound. There's just one particle there. Okay? Sodium chloride, that's 2 particles. So you would say 0.18 times 2 would be the actual molarity that you'd be using there. Aluminum nitrate, you have how many particles? 4. So that's 4 times 0.1. So that's up to 40. That's going to be bigger than the, I'm sorry, that's 0.4. That's going to be greater than the 0.35. Okay, so it's winning there. The other one was 0.36, right, for the sodium chloride. How many particles for K2CO3? So 3 times 0.15. 0.45. Okay. And then for the last one, 3. So that's only 0.33.
Wouldn't we just be looking at the ionic chart, like the ionic, polar, and the non-polar? Wouldn't we just look at that?
Now for this. This is simply, is it ionic or covalent? If it's covalent, the von Hoff factor is 1. It doesn't affect the, yes, I. It doesn't affect the molality, okay? But if it's ionic, like the rest of everything, so the first one's covalent, but everything else is ionic. How do you identify something that's ionic or covalent? Metal, non-metal, or just all non-metals?
Why are you multiplying? Why are you just multiplying the molality by the particles? What can you do that for again?
For colligative properties, for things like osmotic pressure, boiling point, freezing point,
Which number are we
depressions.
looking at?
Number 19.
So why did you just go through and multiply the molalities by the particles?
Because that's, if it's ionic,
Then
you have to change it. Because ionic things break apart.
Covalent is already in the molecular.
It stays together. When you dissolve that into a solution, it stays together. But when you dissolve sodium chloride in solution, it breaks up into,
So the first one would stay 0.35.
that's right,
The second one you would multiply by 2.
that's right,
Third one you would multiply by however many particles that is.
4, that's right.
4.
3 nitrates, 1 aluminum. So that's 4.
Yeah. Next one will stay the same? No.
No, it's 3 particles, K2CO3, 1 carbonate,
That's how many?
2,
Is it 3 particles?
it's 3 particles. 1 carbonate, 2 potassiums. That's right. And the last one is 2 sodiums and 1 sulfate. So it's 3 also.
And then after you do that,
Then you plug it into the equations.
sorry?
Then you would use it in the equations. So let's see. Do I have the equations open right here? What is going on with this page? Okay, do you see? This might help you, Andrea. See how the equations are written?
Yeah.
Okay, so you see I? That's the number of particles. If it's covalent, I is 1. If it's ionic, you put the number of particles for I. And then you would calculate this. Okay?
And that's when you're trying to find, what is this question coming from?
This is change in boiling temperatures or
no,
change in freezing
is it like a
temperatures.
homework that we have?
Yeah. This is an old homework I pulled up. Chapter 11.
Number 19?
That is number 19. Okay. So which of the following aqueous solutions has the highest osmotic pressure? Okay. So that's the same kind of question. Okay, looking at the number of particles and how they would affect it. Okay, I guess it must be chapter 10 that has the boiling or the heating curves. So let's look at chapter 10. That's not the best example. Okay, here we go. The heat capacity. Do you guys want to do this after a break or before it? After break? Chapter 10. I went back chapter 10 to find it. It's in chapter 10. That's the question. So we'll take a break and then we'll come back and we'll answer this. I just asked, do you guys want to take a break or do you want to do this first? And it was said break.
Oh, okay.
Okay, so.
Well, your vote doesn't count.
Whatever, Patrick, it's fine. You don't even need to pass this.
What'd you say?
Yeah, you do. If I get that grade on, it's my grade on drive 10 points
Do you have the final exam on Canvas yet?
Not yet.
Throw it on there so I can type in a grade and see what
say I got a
you
zero.
get.
Oh, there's not a placeholder either?
No, it's not even on there.
Okay. Yeah, I can do that.
Just like to know what I need to get.
Yeah, I'd like to know what actually is my bare minimum.
So I can shoot for that bare minimum. Chalk up a couple L's and chapters.
Oh, yeah. Wait, do you average the midterm and the final?
Record this. Okay, so we're going to go from 67 degrees Celsius and we're going to hit a plateau at 100 degrees Celsius. Okay?
Are we going to vapor?
We're just going to go to 100. Yes. It's going to heat capacity of liquid. So if it, yes, that's why they give us the delta H of vaporization. Otherwise we wouldn't need it. Okay? So we're going to go 67 degrees Celsius here for 1 gram of water. 1 gram of water. Let's convert it to moles. That's 18 grams per every 1 mole. What is that?
118.
It's 0.0555.
0.0555? 6. Okay. Moles. H2O. Okay, so I'm going to use that later, but here Q equals MCAT. Okay. I'm going to say Q equals 1 for the mass of the water times 4.184 joules per gram time degrees Celsius times the change in temperature, which is what?
100 minus 67.
100 minus 67, final minus initial, and we're going up. So we're going to do 100 minus 67. What? So it's a positive 33 degrees Celsius temperature change. Okay, so 4.184 times 33. Q1 equals joules. The grams canceled here. So that's how many joules we got from the first process. Okay, now for Q2, Q2 here is equal to the moles, good, converted to the kilojoules from the moles using the delta H of vaporization. So we have, for Q2, we have 0.056 moles, and we're going to convert that to the kilojoules from the moles. And the delta H of vaporization is 40.7 kilojoules per mole. Those are the units of it. So we have 40.7 over 1 mole. So we get 0.56 times 40.7. 2.26 kilojoules. Okay. Now we need to add Q1 plus Q2. But we need to convert one to joules or the other one to kilojoules. It doesn't matter which way you go. But in the end, you need to report your answer in kilojoules. Okay? So let's go ahead and take the 138 joules and convert it to kilojoules. So we have 2.26 kilojoules for Q2 plus 0.138 kilojoules for Q1, and that's going to equal what?
2.4 or 2.399.
2.39 kilojoules. Okay? So that's how we're going to get through that heating curve. Okay, so you okay with that? If it was more curves, then you would just, add just keep adding all the Q's that you find. But for every slope, you find a Q using Q equals MCAT. For every plateau, you use the delta H that they provide you. It's either the delta H of vaporization if it's vaporizing it. If it's liquid to solid, that's the delta H of fusion. Okay, so you would need okay, so here you would use a delta H of fusion, and here you would use the delta H of vaporization. Okay, because you're vaporizing.
And the specific heats will be different.
They will. You're going to have a different specific heat at each step. That's right. So if we kept going above 100, we would use a different specific heat for vapor, water vapor, than we do for water liquid. Okay? And they specified that the heat capacity of liquid water is 4.184 joules. If it was for ice, it would be even a different C, heat capacity. Okay, so let's see if we have any good ones from the homeworks.
Yeah.
Okay, what is the boiling point of a solution of 12.0 grams of urea in 165 grams of water? Okay, so 12.0 grams urea, CH4N2O, CH4N2O, and it's 165 grams of H2O, 165.0 grams of H2O. So we're changing the freezing point of water. The KB for water is 0.52 degrees Celsius per molal. 0.52 degrees Celsius per molality. Okay, so the equation delta TB equals the KB molal I, which we don't have to worry about here because what's the von Hoff factor? 1, because this is a covalent compound, urea. Okay, so von Hoff factor is 1. So we just need the KB times the molality. Molality equals what? Oh, I'm sorry. Okay, we have moles of the solid over the kilograms of the solvent. Okay, so we need to find the moles of the solute. So we need to convert these 12.0 grams of CH4 N2O into moles from the grams. Did somebody find the mass already? 58. Okay. 12 divided by 58.
No, 60 grams. Doesn't throw it off that much.
Oh, 58 is 60 grams. 0.2 moles. Okay? So we have 0.2 moles. That's a nice easy number to work with. Okay? So 0.2 moles and our kilograms of solvent. They tell us we have 165 grams, so we convert that to kilograms. So we get 0.2 moles over 0.165 kilograms. So 0.2 divided by 0.165. 1.2 molal. Okay? Alright, so now we just have to say delta TB equals 0.52 degrees Celsius per molal times 1.2 molal. Molalities cancel. I'm left with degrees Celsius change, and my delta TB equals what? 0.63 degrees Celsius. So, what is the freezing, or sorry, what is this? Boiling? What is the new boiling temperature? Water boils at what temperature? 100. So the new boiling temperature is 100.63 degrees Celsius. Okay?
Wait, why couldn't you just, so it's delta T equals KB times amount of molality, why can't you just, right, is that the equation?
That's the equation.
If you already have the KB and the molality, why don't you just multiply those together and that's your...
We did. That's exactly
Oh,
what
you
we
just-
did.
Okay.
0.52 times 1.2.
Oh, never mind.
And that equals 0.63. And so that means your boiling temperature change is by 0.63 degrees Celsius, so it's going to go from 100 to 100.63 degrees Celsius.
And our 0.52 at the top, that's our KB?
Yes.
Okay.
KB equals 0.52 degrees Celsius per molal.
And then so if we had, like, let's just say instead of urea, it was like sodium chloride. So then that would change it because the ion would be 2, correct?
Yeah. That's right. So then instead of it being
And then plus
0.2, so you would, let's say you still have 0.2 moles. Okay, or your molality was 1.2. You would just say 1.2 times 2.
Okay.
So it'd be 0.52 times 1.2 times 2
Okay.
if it was for sodium chloride. If they didn't give you the actual von Hoff factor, which is like 1.9 or something.
And then if that came out negative, you subtract it from that, right? If you get a negative.
Negative.
delta T,
How are you going to get a negative delta T?
you can't get a negative delta T?
Because anytime you add
Be
something,
cool.
it's gonna raise
that would be cool. Okay, the KB is always a positive number, right? 0.52. And then your molality is always going to be a positive number, right?
Very well.
So you won't get a negative.
same thing for freezing point? You always just.
Because
subtract
the
it?
thing about boiling point is it always raises.
Always goes up.
It never goes down. Your boiling point always raises. The freezing point always depresses.
Very well.
So you're going to get a positive number for freezing point, but you're going to subtract it from your 0 degrees Celsius. So if this was freezing point, it would be negative 0.63 degrees Celsius. That would be the new freezing temperature. Okay?
If it's water.
If it's water. If it's cyclohexane, then it's from, 6 or degrees Celsius. What do we do? 6 or something like that.
So if it is water, would they give us the boiling point and like they would say?
They would give it to you, right? But for water, they expect that you know the temperatures that water boils and freezes at. Okay? But anything else, they wouldn't expect that. You can.
What chapter is this?
Chapter 11. Like literally, like that's what it was. Which was like the very beginning.
So long.
I know, it seems like it was forever ago, but it's only been a few weeks. Okay. Let's look at some 13.
What 13?
Rate.
Oh, yeah. What about like a, I don't know, rate of disappearance? Did we go for that?
Yeah, I don't remember.
No?
Might have.
Did you just make something up?
Oh, wait, no, you didn't make it. But that has to do with this. Are you talking about the stoichiometry, how it relates to the rates of disappearance and appearance of things?
I mean, I just don't like remember. Yeah. I don't remember what you said about it.
Where it's like,
It was like minus 1/2 rate or something.
for the,
I don't know, I wrote it in my
like the
notes.
first and second,
It's on chapter 12.
the rate of.
The
So
first
it's right
one.
here.
Is it? That was 13?
Yeah, go down a little.
That was 13? Yeah. Is that rate? Is that rate of disappearance? That's what I'm saying.
Okay. Oh, this is equilibrium.
It's chapter 12.
Chapter 12, excuse me. Chapter 12.
Is it?
Chapter 12 is right.
I don't know.
Excuse me. Chapter 12. Okay. Okay, so chlorine dioxide reacts in basic water to form chloride and chlorate according to the following reaction. The initial rate of disappearance of chlorine dioxide was determined to be 2.30 times 10 to the negative 1 molar. What is the initial rate of appearance of the chlorite ion under these same conditions? Okay, so we're looking at what are the relationships. So the disappearance of chlorine dioxide, so ClO2. So how would I relate those two things?
2 to 1.
Okay. So with rate, we want to write them in this way: 1/2, negative 1/2. The rate. Let's just say just say the rate of ClO2 equals. Okay. And we're going to go to what?
Chloride.
What is the initial rate of appearance of the chlorite? Chlorite, which is ClO2 ion. Okay, equals ClO2 minus equals the rate of ClO2. So we know the rate of which thing?
Dioxide.
Of this one, right? So if I take half of that, half the rate of ClO2, then that equals the rate of ClO2 minus. Okay, so that's how I relate them stoichiometrically. So I just multiply that rate that they gave us by 1/2. So 2.35 times 10 to the negative 1 times 0.5, and that's going to equal the rate of appearance of the chlorite ion.
So the sign doesn't matter, right? The sign is just saying it's disappearing.
Appearing and disappearing, that's what it means. Mhm.
So it's just stoichiometry too,
It is.
in this.
It is stoichiometry.
Unless they're on the same side, right? Can you do the next one?
It's going to be the same way if it's on. So here, for this reaction at a particular time, what is the change in the Br minus? What is the change in the rate? Okay, yeah, so you see how they're writing this, the change in the BrO3 minus over change in time? All that means is rate. What is the rate? So you can simplify that term to be the rate of BrO3 minus.
This is negative. That's because it's on reactant.
Well, so the negative is better than one half of the
It's a term. It's the disappearance of BrO3 minus equals 1.5 times 10 negative 2. It's per second. Yep. Okay. So what is the rate of Br minus? Okay.
By 5.
So now I have to look at their relationship. What is their relationship? So BrO3 and to 5Br. Okay, so 1/5 the rate of Br minus is equal to the rate of BrO3 minus. Okay, and we can even say the minus is there because they're both reactants. So how do I figure it out? I just multiply the rate of BrO3 times 5 because that's what I was given, right? So 1/5 the rate of Br minus is equal to 1.5 times 10 to the negative 2 molar per second because that's the rate they gave me, right? So I just multiply it by 5 and that will equal the rate of Br minus. Okay? Okay, we okay with those?
So it's usually gonna be on one side, like, if they're asking about a reactant, they're both gonna be on the same side. Does that not matter?
It doesn't really matter. If it's reactant, then the term is negative for each side because it's reactant. But just realize that's mostly just a term to tell you what's happening. Okay. That's kind of all the same. So remember for a rate law, so if the concentration of B is doubled while that of A is unchanged, by what factor will the rate of the reaction increase? So here they give you the rate law, which means that they told you the orders of the reactants. Okay? So if the concentration of B is doubled, so if you get a question like this, you could actually put numbers in there, and that's one of the best ways for you to really make sure you're getting the right answer. Okay? So rate equals K times the concentration of A times the concentration of B cubed. Okay? So, so let's just say K is 1, the rate constant is 1, A is 1, and B is 1. So what does our rate equal? 1. Because this is cubed. Okay? Now, they tell me if the concentration of B is doubled while that of A is unchanged, so I can double B. So equals 1 times 2 cubed. Okay? 8. This is 8. So it increased by what? By a factor of 8. Okay? So by what factor will the rate of reaction increase? By a factor of 8. Okay, so that's a really easy way to see that happening. Okay. All right, let's look at this one. Chlorine dioxide reacts in basic water to form chlorite and chlorate according to the following chemical equation. A kinetic study of the reaction under a certain set of conditions yielded the data below. So with this, we want to find the rate law. Rate equals K times the concentrations raised to their orders. The concentrations of the reactants raised to their orders. So we need to find the orders from the data here. Okay? So experiment 1 to experiment 2, hydroxide was held constant, right? So because hydroxide is held constant, and that of ClO2 changes, I can relate it to the change in the rate. I can relate it to the change of the rate. Okay, so from experiment 2 to experiment 1, it doubles the concentration of ClO2, right? And what happens to the rate between experiment 2 to experiment 1?
It's times 4.
It's 4? So, okay. So it changes by a factor of 4. Okay, so we double it and it changes by a factor of 4. So x, 2 to the x equals 4. So what is the order? Second order. All right. So this is it. So for the ClO2, it's going to be second order. So already I can see the only 2 possible answers. Okay. Now let's find it for OH. So from experiment 2 and 3, so from experiment 2 to experiment 3, I double the concentration of OH minus, and what happens to the rate? The rate also doubles. Okay? So the concentration doubles, the rate doubles, that's what order? First order. Okay? So then I can see that this would be the correct answer, right? So it doubles the concentration, or sorry, ClO2 is second order, OH is first order. So that's how I find the rate constant. Okay? Okay, so here we have a 25 degrees Celsius. The rate constant for the first order decomposition of a pesticide solution is 6.4 times 10⁻³ minutes per minute. If the starting concentration of pesticide is 0.0314, what concentration will remain after 62 minutes? Okay, they told us this is a first order decomposition reaction. Okay, the temperature is 25 degrees Celsius. They want us to find out how much is remaining after 62.0 minutes. That means I need the rate constant. I need a rate constant. I have an initial concentration. I have everything I need. I can simply use the equation. So here, if I go to my rate equations, it's a first order. So I'm going to be using the natural log of A over of A at time over A initial equals the negative KT. That's the equation I'm going to use. And what am I solving for? A at time. What is the concentration at the time? That's what I want to know. Okay? So, let's see here. Natural log of A time. Try and get this right. Over. So it's a ratio over A naught. Oops, not A naught. A initial equals negative KT.
Formula. We have natural log of A time equals negative KT plus natural log of A initial.
Well, that's just rearranged, right?
No, because that would be times. That would be multiplied, right?
This one?
Yeah, that one right there. So that has it as minus KT, so I'll do the same thing. The other one, you have a natural log of A over natural log of A, which then that would be negative KT times natural log of A.
Are you saying the one on the reference sheet is
The one on
wrong?
the reference sheet's wrong.
This one's wrong.
Yes. That should be natural log of A time minus natural log of A of naught.
It's the natural log of A naught over, or AT over A naught, is what it's supposed to be, like a whole combined. ln
Oh.
of A naught divided by, or AT.
So the natural log of AT divided by, so it's
Oh,
natural
I'm
log
sorry.
of AT over A naught
Yeah.
inside.
Inside, all inside.
Is that better?
Oh, yeah.
Sorry. Hey, I wrote that wrong. Right there wrong. This is a whole term.
Yeah, it's basically saying ln of AT minus ln of A naught, right?
Right.
Because
Yes.
the
That's what it's saying.
The logarithmic properties.
I'm sorry. Did I just wrote it down wrong. Right there. But
For those of you that are pre-calc right now,
okay, so I can see how that could be confusing on this. Okay.
I see it.
Okay. Because okay. Let me. I'll put that one better on there, so it's not so confusing.
What?
Okay. So we want to use this. We want to solve for. We want to solve for A at time. Okay. We have our K. Whoops, no. Where are we? Here we are. Okay, which is 6.4 times 10 negative 3. So K is 6.4 times 10 to the negative 3 per minute. And the time that we're using is also in minutes, right? 62 minutes. 62 minutes equals natural log of 0.03. If the starting concentration is 0.0314. Over 0. Okay, and then we would just solve for our x here.
Times 0.
Let me see. Okay, so are you guys finding this? Anybody finding it? What are you getting?
So would it be x equals p to the
That's some tough algebra right there.
Well, e to the ratio.
Isn't it easier to just set it up the other way?
Yeah.
Yeah, which way did you set it up?
I think I'm just.
Natural log of-
The natural log of A equals negative kt plus the natural log of A.
Okay, natural log of a.
T at time.
All right.
Negative kt.
So-
Yeah, same thing.
Yeah. Yeah, you would. So. Basically. So you want it written like this.
That's how we learned it.
Okay, that's fine. We can do that. Okay. Where's my? Why am I missing all my? Oh, yes. From here?
Yeah.
Oh, why is that one like? Okay.
Yeah, that one.
That's fine.
Well, that's because one of them. Natural log.
I'm just wondering why I don't have all my options up top here. Where are they? You just can't see them? For some reason?
Get 'em back.
Mm-hmm. Then I would really be in trouble.
I agree.
Okay. Okay, ln, natural log of that.
Just negative
Negative kt natural log ln of a naught.
plus
I'm sorry. Did I lose it? Shift plus. Oh yeah, okay. Was that the only one the other ones are okay, right?
Yeah.
Yes.
Okay, that was the only one that was confusing. Okay, there. So that'll make it easier because you'll just take the natural log of the a naught initially, and then you'll easily be able to, and then yes, you'll just send it up to that. Okay, here you could take the natural log of that and be left with the natural log of x, right? That would probably be the way that you would do it. Okay. So, what do we have? 6.4 times 10 to the negative 3 minutes times 62 minutes. Natural log of a. Natural log of 0.0314 equals natural log of x. So yeah, you can simplify all that, right? Simplify all that, and then x equals e to the everything up there. 0.0314 minus 6.4 times 10 to the 3 times 62.
Fun stuff.
Okay. You guys finding something? Okay. Moment. Okay.
Are we doing this again tomorrow?
One last time.
No answer?
Yeah. So tomorrow's your last chance. So, ideally you guys would go home and really like focus in on what you need some help on. And come prepared to go over and bring some examples with you, because that really helps when you have something prepared for me to go over with you.
I mean, we said chapter 10 through 17.